Hello, my name is Zeus Negron, and this is the Group 17 project presentation, Joint Communications Radar Signal Design in Millimeter Wave Frequencies. The extremely high frequency spectrum has traditionally been the realm of satellite communications and military radar. Introduction of 5G technology raises concern about spectrum congestion, however. Spectrum congestion, which is basically when signals compete for frequencies in a frequency band, leads to interference. And with those legacy applications like the military radar already in place, lack of available frequencies could stunt 5G tech. A preemptive solution to this is the co-design, the Joint Communications Radar design. So basically designs of signals capable of transmitting data while simultaneously performing location via radar. This project will specifically target the 71 to 76 gigahertz frequency band in designing a signal capable of servicing both data communication and radar. This will encompass finding specific waveforms and developing specific methodologies of transmission. Such a signal would relieve the threat of spectrum congestion and could be ideal for several new applications. That would be something such as autonomous vehicles, where it would streamline the location sensing of nearby objects and vehicles while maintaining the vehicle-to-vehicle communication that's essential for those to work. There's also the area of traffic management, e-health, and next-gen smart factories. If you can imagine robots being able to communicate with each other and not run into each other using only one frequency. So the way this would work, if you can follow the box diagram from the top down here, firstly, a signal is generated. This would be some waveform that is suitable both for communications and radar. And that is disseminated to the two separate subsystems. The communications system takes a wave, modulates the signal to accommodate whatever data is being transmitted, and then transmits that signal. The radar takes the same waveform, okay, and pulses it out to do radar echolocation. Okay, both of these systems should work independently of each other, but we are also integrating them to where we should send one signal only that does both things. It can be used for radar and send data transmission. Okay, and then ultimately it will be received on another base station receiving antenna, and the performance of the signal there will be analyzed to see how much data was lost, if any, and what kind of radar image we received. So this diagram shows one possible methodology of transmission. If you can follow the diagram from the bottom up this time, we have two separate transmitting antennas, one for communications, one for radar. And up top we have two separate receiving antennas, one for communications, one for radar. The communications and radar transmitters are both transmitting a signal, their signal, at the same time. And this signal is, of course, on the same frequency. The receiving antennas, for instance, the communications receiver, will receive the communications transmission, but it will also receive the radar transmission. The radar transmission will hopefully be filtered out, and then the communications receiver will receive only the modulated communication signal. Likewise, on the other end, the radar receiver is going to receive both the radar transmission and the communication signal transmission. There, the communication signal will be filtered out and the radar signal alone will be received. The subsystem that I am personally taking lead on is signal creation. The ultimate goal of this project is to find suitable waveforms for joint communications and radar. There's different types of waveforms. They come in different shapes. There's a sinusoidal, square, sawtooth, triangle waves, each with their own benefits and drawbacks, which for this specific project, we will have to do a lot of testing and experimenting with to find what waveform is suitable, or if there's some hybrid waveform that we can possibly come up with. As far as generation of these waveforms, we will be using MATLAB. And luckily, MATLAB has several built-in functions for creating waveforms that that are very helpful. It's as easy as plugging in a waveform formula with, obviously, you've got the variables of frequency and amplitude and phase shift, but those are plugged into MATLAB, and simple code, and it pushes out a wave. Now, unfortunately, there is no built-in support for 5G in standard MATLAB. I think the highest frequency waveform that you can create is somewhere around 6 gigahertz, which is very short of the spectrum, the bandwidth that we'll be working on. So, for that reason, we will be using MATLAB's 5G toolbox. It has some additional functions for waveform creation, as well as a waveform generator app that we'll do some experimenting with. Now, the method of signal creation has yet to be determined. We're not sure if we're going to be using an intermediate frequency signal and either step that up to EHF, or if we're just going to use a EHF signal. If we can generate that using the waveform generator app or some other functions with the 5G toolbox, we'll do that. We have developed some functions on just standard MATLAB that allow for user variable input, shape, frequency, amplitude, etc., to create signals. We are that far along on our code. Either way, the finished product, the output of a signal, will be published on an M file, and that will be pushed out to the communications and radar subsystems.
My name is Daniel Guzzi, and one subsystem I will be contributing to is the communication subsystem. This diagram shows the general layout of the transmission system. And while it is not necessarily the only part of the communication system I will be working on, it is the part I will speak about. First, there's the source encoding component. When preparing to transmit data, it replaces sequences of redundant code with shorter corresponding code compiled at random. This compresses the data for more efficient communications. Part of the challenge will be identifying an optimal encoding scheme, whether it means finding one that exists in the functions of MATLAB or constructing one from scratch. After this comes channel encoding. This is the process by which lines of code are replaced with specific corresponding code words of greater length to increase redundancy. This technique is used to reduce data corruption during transmission. Unlike in the original source code, this redundancy is controlled, so the transmitter and receiver both have access to the information. If a code book, which is a set of code words, needs to be made from scratch, we will need to determine the statistical effectiveness of the code words in presence of corruption. Then there is the portion of the transmission subsystem that will likely receive the most attention, modulation. This is the process by which the system modifies properties of a sinusoid to serve as a carrier signal for data to be transferred. Among the methods involved is the amplitude shift keying scheme. In this scheme, the amplitude of the signal is altered to represent different values. Then there is phase shift keying, the simplest form of which is binary PSK or BPSK for short, which has either no phase change or a 180-degree phase change. Furthermore, there is the quadrature amplitude modulation, a hybrid method that combines the modulation methods for amplitude and phase shift keying, creating a greater variety of values. Finally, there is frequency shift keying. This method is one in which carrier frequency can be increased or decreased by one of n possible frequencies, where each new frequency corresponds to a different symbol. Proper modulation of data is meant to make the most efficient use of the wave spectrum for transmitting data. Then there is the digital to analog converter and the RF circuit, which are likely already included in the provided millimeter wave transceiver system. Finally, the transmission antenna can broadcast the converted signal to the receiver antenna on the other system. Among some other components that may be involved are the MATLAB 5G and/or MATLAB communications toolboxes. These include functions for modulation and demodulation in communication signals. Also, the 5G toolbox is designed specifically for simulating and analyzing end-to-end 5G communication.
Hello, everybody. My name is Cedric Clement, and I will be covering the communication aspect of this project. More specifically, I will be focusing on the receiving part of the communication aspect, the wireless communication. Because as some of you might know, wireless communication, that means that there is a transmission of some sort of information that uses an antenna to transmit that information. And on the other hand, there is a receiving antenna that receives whatever message that we had transmitted. If you look at the diagram that is being presented from right to left, you can see that we do have the RX antenna. By the way, RX, this is usually how the receiving antenna is being denoted, and the transmission antenna is usually denoted as TX. So for the RX, from right to left, RX antenna, then we do have our RF circuit, our analog to digital converter, our demodulation, our channel decoding, our source decoding, and hopefully whatever data that we do find after all of these steps at the receiving end, it does matches what we intended to send. And we will cover more of these in the next couple of minutes as we progress. Let's cover and try to find out what exactly is happening at the receiving end of the antenna. We first can see, if you recall from our previous diagram, the first thing that we did notice was the RF circuit box, and we had filters, down converter, and amplifiers included in that. What this is for is whenever we have the signal coming into the antenna, if the signal comes in too weak, then we definitely need to amplify it. If the signal comes in a particular form, but this is not the form that we actually need, then we probably will have to use some sort of filter. It could be a low pass filter, a high pass filter, whichever type of filter that will allow us to work with whatever we need to work with. Then we might use either a filter, an amplifier, or a down converter with that. What happens at the receiving end of the antenna as well is that once the signal has been transmitted, it travels its course, often directional to a destination. Now, signals can scatter around. However, for the purpose of this main project, the equipment that we are using at the lab here at FAU, our antennas are very much directional, meaning that we definitely have to position them in a specific way in order for them to work as well. So, for our project, yes, we will be having transmission antennas, but our destination will be whichever position that our receiver is positioned at. And next, we can go ahead and we can see that we do have an analog to digital converter. The reason for that is in the real world, information such as time, distance, and a lot of other information that we perceive as human beings or that we know of, they are usually analog values. So at the transmission side, we did have a digital to analog converter, meaning whichever information that we did have and our software was digital, then we needed to convert that to analog as the signal was being transmitted wirelessly from the transmitter to the receiver. So this is why we also need a an analog to digital converter to convert the signal back into some sort of digital form that our machines can know how to communicate or how to process them in a much more efficient way. Then we proceed into the demodulation aspect of it, which is the opposite of modulation. Then there is channel decoding and source decoding. But most importantly, why we do all of these things, it is because the data that we are going to be received doesn't necessarily mean that this is what was transmitted. In other words, there will be errors due to real life situations and characteristics that needs to be factored in. And one of the best way to that we mitigate with that is to use Shannon's limit. Shannon limits or Shannon capacity is an incredible piece of theory that tells us how many bits per second or error free information we can send. And as you can see, there is this formula where all of the components are defined, and this is what is known as Shannon limits or Shannon capacity.
A radar is radar detection and ranging systems. The job of a radar is to detect radio energy being transmitted to a specific target, then returning as an echo. In a joint radar communication system, the two will overlap and it's in a time or frequency domain. Here below are lists of the different types of radar there are, the frequencies that comes with the radar, the aim or what the radar is trying to give off, the applications where the radar is used, and basically what we'll do is some radars will have, the ones we are working with will have a high frequency, very high frequency, or extra high frequency, and we will base our usage of the radar based off the location and atmosphere that we are in geographically. So if we're tracking vehicles or anything with the vehicle, it'll be airborne or spaceborne or even landborne. And our aim for that is to detect a certain object, track the location of the object, surveillance, which basically shows us where the spot of the object is, and our overall goal for radar is basically to always have privacy that goes for what it's being used for or the classification of the type of radar we are using. And since our main focus is 5G, we definitely want to have privacy when it in regards to 5G and mobile ability. Within some radars, different applications that are used includes military, air control, remote sensing, ground traffic, and space. So if we're using a military radar, we would use it for air defense, target detection, target recognition, and weapon control. For air traffic, it would be air traffic near airports, surveillance radar used to show the position of an aircraft and the airport terminals, and it guides the aircrafts through bad weather and just used for precision and specific locations on other aircrafts or other locations revolving around where that aircraft would be. In remote sensing, it'll be weather observations. For ground traffic, it'll be speeding. The police will use it for people who are speeding, movements of cars. And in space, it'll be guiding space vehicles for safety, detecting and tracking satellites, and monitoring meteoroids. So the specifics of our radar that we will be using is we basically want it to detect the location of an object 30 meters away from the system that will be given with the technology that will be given from our sponsor. We don't know the application yet as of right now. The project overlook, or what we want the radar to do, is sense the parameters of the radar and communication levels of an object and the signals. So basically just sensing the precise movement and the precise um, recognition of the radar and the communication links. Develop an algorithm of each subsystem so they coexist, so ensuring that the communication is on track and ensuring that the radar is detecting the communication, and they work independently but they coexist, so they overlap over each other. So both of them are working together at the end, and then we stimulate the results based on the signals and parameters given to develop a system that provides accurate information for the radar/communication links to track a specific location of an object. So that's the overview of the entire system that we're using. In regards to the radar will detect our object, it will locate it, track it, and then we will communicate with it and bounce the signals that we get from the object to the radar and detract basically what we're looking for with the time frame of the radar and communication, how long is the distance, how long does it take for the communication to basically give us an alert. Within this radar, the one of the sensors that we will be using is called a frequency modulated continuous wave sensor. It is technology that will allow us to detect an object within wide distances and helps us detect the motion and velocity of that object. Right below it is an equation used for an antenna system. So initially what we are trying to do is set a radar at one end of a spectrum, give it an antenna, have the wavelengths bounce off of it, detect our object or our other part of the system, which is the communication part, communicate with the object, echo the wavelengths back in a sense to signal that there was some sort of connection or like detect a response from the object and detect the higher range, the higher radar range. to sense that there was some recognition in the object in the radar to provide us with a system.
Now we come to the analysis of performance section. This will be done by James Koss and will describe this software component of our project. We intend to use the metrics such as bit error rate, symbol error vector magnitude, and signal-to-noise ratio, which is used in both communications and radar, to demonstrate the performance of the various signals we design. We intend to compare the data to analyze the signals in order to determine which is performed best for the communication function, the radar function, and the joint communication radar function. The slides that follow will detail the various metrics and the implementation of each. First up, we begin with bit error rate and symbol error rate. These metrics will be used to determine the performance of the communication software component of our project. So without modulation, we cannot transmit data using wireless signals, but beyond the basic modulation that results in 1 bit per symbol, these two error rates will diverge, otherwise they are the same. Since the communication subsystem can use various types of signal modulation to accomplish the high data rate promise of millimeter wave frequencies, we can implement both symbol and bit error rate to determine how well these different types of modulation perform. The symbol error rate will show how many symbols in the received signal differ from the transmitted signal. For example, a symbol that carries 2 bits might be transmitted as 00 and received as 01. What we see in the difference between 00 and 01 is an error rate of 50%, and the difference between 00 and 11 is a 100% error rate. So this can be substantial. When you compare it over the entire transmission, you can see how bit error rate and symbol error rate diverge. Now, bit error rate will show you precisely how many bits in the received signal differ from the transmitted signal. And again, there's a substantial difference between receiving 01 and receiving 11 when sending 00. Ultimately, this is something that's substantial for us to watch, because as we move through the various modulations, like 16 quadrature, 64 quadrature, or 256 quadrature modulation types, you end up with more bits per symbol and subsequently more variations in the bit error rate when a received symbol doesn't match the transmitted symbol. Next, we proceed to error vector magnitude. So we intend to employ this metric to locate issues such as phase noise and IQ imbalance, but it can also assist with determining amplitude nonlinearity and filter distortion. Increases to phase noise results in increased interference among subcarriers, which impairs demodulation performance. IQ imbalance describes when the in-phase and quadrature components of a modulated signal experience distortion of amplitude, phase, or both. The bit error rate and error vector magnitude metrics are similar in that the farther a received signal falls from the ideal symbol location that it represents, the closer it is to falling within the decision boundary of another ideal symbol location. A larger bit error rate coincides with this phenomenon. This relationship, though, might break down at higher levels of distortion because a received signal in another decision boundary might be close enough to improve the error vector magnitude for that ideal symbol location while being assigned the incorrect symbol, which thus increases the bit error rate. In-phase and quadrature signals should be orthogonal and with the same amplitude, but in practice this is not always the case. The degree to which they are off contributes to the distance from the ideal symbol location at which the received signal arrives. Now we arrive to signal-to-noise ratio using modulation error ratio as applies to communications. And using this metric, we will be able to determine the signal quality when used for data communication. A higher signal-to-noise ratio indicates higher signal strength when compared to noise, and we will aim for a higher signal-to-noise ratio as it correlates to increased throughput. Higher throughput is important to achieve because it means fewer bits lost and fewer retransmissions of the signal. We will look for changes to signal-to-noise ratio that arise due to signal waveform, modulation type, distance the signal must travel before being received, and presence of environmental interference, among other potential considerations. Essentially, we'll be looking to observe the susceptibility to noise of the 71 to 76 gigahertz band and whether certain waveforms and modulation types are affected more by noise than others. And ultimately, we need to understand the range up to which the signal can effectively operate for data communications. The goal is to locate maximal signal-to-noise ratio for data transmission without hindering the radar functionality. Therefore, we must be mindful of performance trade-offs. Finally, we've arrived to signal-to-noise ratio using receiver operating characteristic curves, as applies to radar. Signal-to-noise ratio is set for a given range by using the probability of detection in conjunction with the probability of false alarm. Ultimately, we need to dial in this signal-to-noise ratio in order to be effective with radar and communications, so using the ROC in this way will speed our analysis of the signals to locate the most viable options. Our designs will need to be tested in both single pulse and multiple pulse detection radar implementations to determine the viability of each. And as we proceed through our testing process, we will likely visualize the results using a receiver operating characteristic curve to demonstrate the performance of each signal and corresponding signal-to-noise ratio. The benefits of using the ROC in this way come in the form of being able to plot one signal with different signal-to-noise ratio values or multiple signals with the same signal-to-noise ratio value. This concludes our project proposal presentation. Listed here and on the next slide are a few of the references we used in compiling this presentation.